let's go ahead and talk about what we're going to be doing for chapter 7. So if you haven't had a chance to think about this yet, it's super useful to be able to think about, right, this idea of iteration, because we're approaching some material that maybe you haven't seen before, and that's okay. It's great when we see new things. So iteration is going to be a great norm that we're practicing, especially towards the end of this week as we make sense of drawing Lewis structures. So the first thing I want you to think about is covalent bonding. So take a moment and in your notes, using your prior knowledge, tell me what you know in terms of ionic bonds and covalent bonds. So see if you can answer this question. What is the difference between an ionic bond and a covalent bond? So take a moment, in your notes, on your whiteboard, just jot down your recollection, your memory of what is the difference between an ionic bond and a covalent bond. And if you're like, I'm not sure if I've heard those terms before, then just go ahead and think about maybe how you might apply what you know from what we've already studied in this class to those two terms. All right. So hopefully you were able to come up with some of the following information. So a covalent bond and an ionic bond. So when we're talking about an ionic bond, we're really talking about the transfer of electrons. So an ionic bond can form cations. So for example, sodium plus, or it can form anions such as chloride minus. And really we're forming these again from the reaction of the outermost valence electron. So that's where, in this case, sodium gives up an electron. And in the case of chloride, it gains an electron. I want to make sure that we have the right understanding of what those plus and minus signs mean. They're always with respect to electrons. And then if we think about what we know about covalent bonds, that's going to be the sharing of electrons. There's actually several different types of covalent bonds. So there are single bonds and double bonds and triple bonds. And probably one of the most important components that we'll start talking about today is the fact that those bonds don't always share electrons equally. So there are some examples of bonds where they are shared equally. Really good example would be the diatomics. So H2, F2, Cl2, Br2 are all examples where if I have the identical two atoms, when they share electrons, they share them equally. And so that would be an example of a nonpolar bond. A polar bond is going to be something where those electrons are shared unequally. We're going to talk about that. That's where we see a difference in electronegativity between two atoms. And so one of the atoms holds more of the electrons typically than the other. And again, this is always going to involve the outermost or the valence electrons. So if we think about then this definition of polar covalent bonding, really important that we actually have a mechanism or a way in which we can identify the extent to which those electrons are shared equally or unequally. So here's a great example. If I have an atom that has a higher electronegativity, it's going to pull the electrons in that bond closer to itself. And so we can think of that as having a partial negative charge. And this Greek symbol that we see here that kind of looks like a D with a hook at the top is the way that we refer to a partial negative charge. So we'll draw this symbol and a negative sign. And the reason why we have to draw the symbol is it's not the same thing as a formal negative charge. This is what they call an induced or a partial negative charge. It doesn't exist all the time, it's there part of the time. And then the other atom would then be electron deficient, and that means it doesn't have as many of the electrons, and so it would have a partial positive charge, and that's why we use this symbol, the positive charge. So it's important that we know those two symbols because that's how we're going to communicate to someone else that there's a difference in electronegativity between two atoms. And so when we think then about bond polarity, it's really going to be based on the difference in electronegativity. So if it's a relatively small difference in electronegativity, say for example, the change in electronegativity here is shown as the difference between 0 and 0.4, then that's what we think of as a nonpolar or a pure covalent bond. You can actually see that here with chlorine, right? So there's two chlorines and they share their electrons equally. You can see how there's really no change in the population density of the electrons. They're distributed equally about both atoms. But then if we have a difference in electronegativity that's between 0.4 and 1.8, then that's where we start to see polar covalent bonds. And so that would be an example of hydrogen and chlorine, where the hydrogen has the partial positive charge because most of the time it doesn't have nearly as many electrons as the chlorine does. Right? And then chlorine here has the partial negative charge because most of the time it has many more electrons than hydrogen. And then if we see a difference in electronegativity that's 1.8 or greater, that's where we assign that the bond would be ionic. And in this case, it's a transfer where 99% of the time, or a really big significant portion of the time, that electron spends with the chloride ion. So these are the three types of bond polarity that we're going to be looking at in chapter 7. And that's going to start to influence the way we think about reactivity. And it's going to help us understand why certain chemical reactions have the outcomes that they do. So our task today is really to think about how we draw something called a Lewis dot structure for the main group elements. So the first thing that we're going to do in order to make sense of this is that in your notes, I'd like for you to be able to determine the valence electrons for each of the following elements. So using a periodic table, or actually there's enough information here that you could use the information that's found here. Go ahead and determine the number of valence electrons for each of the following elements. So part of what I hope you will see is that there is a pattern. So if we think about patterns here, lithium, right, has one electron in the s1 orbital because in its period, it's the leftmost atom. So it has only a single electron that is available. If we compare that with beryllium, we think about its position on the periodic table, it has two electrons. Right? It completely fills the s2 orbital. If we contrast that to boron, that has three electrons, and so it completely fills the s2 orbital, and then it puts one electron into the p orbital. Carbon has four electrons, so it completely fills the s2 orbital, and it puts two electrons in the p orbital. And then nitrogen has 5 electrons, so it's going to completely fill the s2 orbital and put 3 electrons, single electrons, in each of the p orbitals. And then oxygen has 6 valence electrons, so it's going to put 2 in the s2 orbital and then 4 in the p orbital. And then fluorine is going to have 7 valence electrons, 2 in the s2 and 5 in the p orbitals. And then neon is our noble gas, and its configuration is stable. So in this case, it completely fills both the s orbital and the p orbital. So here's the thing that I think is valuable. If you have access to a periodic table, you're going to be able to see the group numbers that are above at the top of the periodic table. I think that's the best guide that you can use for determining valence electrons as a place to start. However, I also recognize that maybe as you're doing these types of problems, right, you might forget that. So it's useful to be able to figure out where relative with respect to its position on the periodic table, you could find these elements and know what their valence electrons are. That's going to be really important because the way that we determine Lewis structures is by starting with the number of valence electrons of each atom. So you're going to get really fluent or comfortable or familiar with identifying where to find valence electrons for each of these atoms because you're going to use it as the first step in this next process that we're going to take a look at. All right. So if we think then about Lewis structures, we have really two different ways that we can represent information. So the first way we represent information is to say that in our model, and a Lewis structure is just a model, it's the way that we represent the positions of electrons and their relationships between atoms. So the electrons that are shared by atoms are what we call bonding pairs. So each bond is made up of two electrons, and that bond is represented by a straight line. So if you're thinking about this, right, your bonding pairs have two electrons and they're represented by a single line. And so that's where we have covalent bonds and they're shared. We typically don't represent ionic bonds with a straight line. We actually usually show the transfer of an electron to the anion and represent the loss of that electron with a positive charge for the cation. So if we then think about the other way we represent information, that's where for our non-bonding electrons, these are electrons that are not shared by atoms and they belong only to one atom, and we call these lone pairs. So they're non-bonding pairs in that they're not involved in a bond, and we simply represent them as usually two dots, and that's what we call a lone pair. So we're going to look at some examples of Lewis structures. In fact, what we just did here, where you have the lithium, the beryllium with these dots, these are Lewis structures for individual atoms. We're going to represent now molecules or compounds with Lewis structures. And we're going to talk about the process that we're going to use to determine our Lewis structures. So the first thing we're going to do is we're going to think about the electronegativity trend. If you remember from class on Monday, one of the things we did was review the periodic trends and how we make sense of them on our periodic table. So the trend for electronegativity is that fluorine is the most electronegative atom. And so if we think about it, our trend goes from the left to the right, increasing. So our hydrogen is going to be less electronegative compared to our fluorine, which is more electronegative. And then our electronegativity is also going to increase from bottom to top. So if I compare iodine, for example, to fluorine, fluorine is much more electronegative than iodine. And if we think about the reasons for that, most of that is because of nuclear shielding. So the larger the nucleus, the stronger the pull of that positive charge. And so if we think about then fluorine, it's important that we notice that, right, fluorine's electrons are very close to the nucleus, right? So there's a very strong pull. And that's, right, if we think about our fluorine, it's also a relatively small nucleus compared to the other components. So electronegativity is one of the first places that we're going to look at. Key here, so helium, neon, argon, we actually can't measure their electronegativities. This is a great example of a place where science comes up against the limits of technology. So if you wanted to go on and study something really fascinating, say for example in graduate school as a chemist, you could think about methods that you could use to measure the electronegativity of atoms like helium or neon or argon. So the reason why we care about electronegativity is because it's going to allow us to predict what type of bond we're forming. Are we forming an ionic bond, a polar covalent bond? What type of bond are we forming? And so we're going to use electronegativity plus the following concept. So we're going to use the octet rule, and that's where our main group elements tend to gain, lose, or share electrons in order to have 8 electrons in their valence shell. There are many exceptions to the octet rule. We're going to talk about several of them here, but this is the general guiding principle. And we've looked at the octet rule when we were first starting to talk about quantum chemistry, when we were talking about the stability of atoms. A good way, I think, to approach this is to think about the following. So we have 2 orbitals. We have the s orbital and the p orbital that are relatively close in proximity to each other with respect to their energies. And so because of that, these are places where we're more likely to find electrons than not. And so this is a good way to be able to think about our principal quantum number. So that's the period. We look to the left of our periodic table. It's the row, for example. So if we looked at the first row, that would be hydrogen and helium. We looked at the second row, that would be lithium, for example. And so those 8 electrons tend to be the groupings or the subshells that we see for electrons with respect to a given atom. So let's look at some of the exceptions, and then I think this will help start to make sense of the octet rule. So one of the exceptions are radicals, and we'll be able to talk a little bit about radical chemistry towards the end of this semester, but radicals are rarer, they're highly unstable compounds, and they have an odd number of electrons. And so if you think about this, the number of electrons so far that we've studied are the 2 electrons that are found in a covalent bond, the 2 electrons that make up a lone pair, and so then a single electron would be an example of a radical. Another example that is an exception to the octet rule is something that is less than an octet. So hydrogen, for example, has a single electron. Its atomic number is 1. And so it shares a single electron. And that electron, say, for example, if I formed a single bond between 2 hydrogens, would make it isoelectronic with helium. So in this case, it would then have 2 electrons. The s orbital would be completely filled. And so that would be an example of something that has less than an octet. And the reason why hydrogen forms bonds is so that it can completely fill that s orbital. If we think about something that's less than an octet that's maybe different than hydrogen or helium, we can also look at boron. So boron has 3 electrons that are engaged in covalent bonds. So those are then 6 valence electrons that can exist around boron, 1 from fluorine, 1 from fluorine, and 1 from fluorine. So I have 3 bonds to fluorine. Those are 3 electrons, plus the 3 electrons that boron has. And so those are, right, then 6 that are available and could react. So if we think about this octet rule, there's the valence electrons that an individual atom has, and then there are the electrons that are shared with that atom in order to satisfy, right, the octet rule. But there are some atoms, boron's a good example, that won't ever have a full octet. Boron won't ever have a complete set of 8 because in this case, it doesn't have enough electrons available. There are also examples of expanded octets. These are typically the main group nonmetals, so to the far right-hand side of the periodic table, and they typically are larger, and they can actually accommodate more than an octet. So these are examples of atoms that can, what we often have as expanded, or they can accommodate more. So our phosphorus, our sulfur are probably the 2 that you should be most familiar with that have expanded octets. So if we're thinking about these exceptions, then we can think about a general set of principles or rules. And here's our octet rule summary. So boron and smaller never have an octet. So these only, okay, can have up to 6 valence electrons in the case of boron, or fewer for all of the other atoms that are in the red boxes. But then carbon, nitrogen, oxygen, and fluorine always have an octet. So these are examples of atoms that really strive when they form bonds to satisfy the octet rule. And then phosphorus, sulfur, chlorine, and bigger atoms always have at least an octet. So anything from P forward can have an expanded octet. So if you want to think about it, neon is really kind of your breaking point. So anything that's smaller than neon, right, will either form an octet or less than an octet. And anything after neon has this ability to typically form an expanded octet. And the ones that, again, I think you should be most familiar with are phosphorus and sulfur. Those are the two that you're most likely to see having expanded octets. So why do we care about octets? Well, that's because it's going to determine what types of bonds we form. And so it's really important that we pay particular attention to how reactive a molecule is. Is it stable? Is it like a noble gas where it has a tendency, right, to be completely filled in terms of its octet and thus satisfied, so less reactive? Or is it a molecule like carbon where, because of its position in the periodic table, it literally is 4 valence electrons, so it wants 4 more in order to have its octet. The really cool part about this is that if you're using your periodic table, then you can identify the most common bonding patterns for your atoms. So we're going to spend a little bit of time on this slide because I think it's really important for you to make sense of this, both drawing it in your notes, but also making sense of the reason behind how you know the number of bonds that an element might have. So for example, hydrogen is always going to form only a single bond. It's never going to have any lone pairs because its atomic number is 1. Thus, it can either be a radical, right, that single electron, but that's pretty reactive. It's going to look for another electron so that it can form a bond. Why does it form that bond? Well, it forms that bond because sharing an electron with another atom gives it a completely filled s orbital. So it has 2 electrons then that satisfy that s orbital. If we look at boron and we think about what's most common for boron, because its atomic number, right, is 3, it has 3 available electrons, it is never going to have lone pairs. Instead, it's much more likely for it to have 3 bonds. So it's going to have 3 covalent bonds. And then you can use the same process to think about carbon. So it's very common for carbon to have 4 bonds. The reason for that, right, is because it has 4 valence electrons. And so it's typically going to form either 4 single bonds, or 2 single bonds and 1 double bond, or 1 single bond and 1 triple bond. Because again, those are all 4 bonds. If you think about it, it's still the same number of electrons. It's carbon getting 8 or having the complete octet. So when someone says that carbon is the atom that all life is built around, that's actually the reason why, because carbon wants to form bonds with anything in order to complete its octet. It's pretty rare, but it does occasionally exist, where you have a carbon with a single lone pair and 3 bonds. If we move on then, and we think about nitrogen and phosphorus, right, and the other elements that are in that group, it's most common for nitrogen to form 3 bonds with 1 lone pair. So if you think about it, nitrogen has 5 valence electrons. It's going to form 3 bonds and 1 lone pair, right? Each of those bonds is 1 electron from nitrogen and then another electron from something else. So that's how nitrogen's 5 valence electrons form bonds. It's also common for nitrogen to have 4 bonds, but then it's going to have a positive charge. We're going to look at how you calculate formal charge in just a moment. If we think about oxygen and sulfur and anything that's in that group, and again, if you're like, wait, what's a group? A group, remember, is vertical up and down in the periodic table. So oxygen most commonly has 2 bonds and 2 lone pairs. So there's a couple of ways you can represent that. It's not uncommon for either the oxygen in the center and the bond on the left and the right, and then the lone pairs above and below, or it's also very common for oxygen to have a double bond and those 2 lone pairs. And so if you think about then what also is possible as an arrangement for oxygen, it can also still have those 3 lone pairs, or 6 valence electrons, right? And it could also then have a single bond. And so remember, anytime we see a bond, the bond that we see also, provides us with, a single electron from that atom, and it also provides us with, the electron from another atom. Then it's pretty rare, it's very rare actually, that we would see oxygen having 3 bonds and a single lone pair. And then if we think about our halogens, it's very common for them to have a single bond and then our lone pairs, so the 3 lone pairs or 6 valence electrons for our halogens. Now, here's the thing. It's really tempting to want to just memorize what these patterns are. But you don't actually have to do that. You don't have to memorize them. You can figure out what the pattern is based on knowing the valence electron. The patterns are really helpful because as you start to draw your Lewis structures, you can rely on those patterns, so you have to do less work. The goal at the end of the day is that you're more comfortable drawing Lewis structures because you know the number of valence electrons, and then if you know the number of valence electrons, you also know, the likelihood of forming single bonds or double bonds or lone pairs. So we're going to do some practice. That's the whole goal of today, is just to get us familiar with and practicing how we draw Lewis structures. So here's what I want you to think about. We're going to start with the carbonate ion. So I'd like for you to think about, what is the formula for a carbonate ion? This is an example of one of the polyatomic ions that you have to know. It was actually a great example of one that we have studied previously, So for other exams, we've done that. You could also, if you're not confident that you know the formula for carbonate, you could actually also look it up in the handout from, oh my goodness, that was a long time ago. But you could look up the formula in the handout from, I think, week 2, where we were taking a look at our polyatomic ions. So take a moment, think about what the formula is for carbonate. And if you're stuck, you can always look it up. So our formula for carbonate should be CO subscript 3. Remember, subscript means the smaller 3 that's lower than the letter. And then a charge of 2 minus. So carbonate is CO3 with a charge of 2 minus. So the first thing that you're going to do when you're studying carbonate is you're actually going to add up the valence electrons. So if you think about the exercise that we did earlier, if you go back in your notes, you can actually find both carbon and oxygen to be able to figure out its valence electrons. Or you can use your periodic table. So here's carbon. In your periodic table, there's the group number 4 that tells you the number of valence electrons of carbon. And there's the group number of oxygen, 6, that tells you the valence electrons for oxygen. So we're going to add those up. If we have 1 carbon, that's 4 valence electrons, plus 3 oxygens, that's 6 valence electrons. And we also have to be really attentive. We want to add in our charge from the carbonate ion. So carbonate has a charge of 2 minus. So that's going to be 4 plus 18, or 3 times 6, which are the valence electrons for oxygen, plus 2. That gives us the total number of valence electrons. Then when we draw our structure, we're going to use that information and we're going to determine the least electronegative atom. So in this case, because carbon is to the left of oxygen in the periodic table, it's our least electronegative atom. So that's where we're using our trend of electronegativity. So here's what that looks like. So we have our CO3 2 minus ion. We have the 4 electrons from carbon, the 6 valence electrons from oxygen, but we have 3 of those. That's what this subscript number 3 means. And we have the 2 from the -2 charge here. So we're going to add that up, and that's going to give us a total of 24 electrons. So when we build our Lewis structure, part of what we're going to build, right, is going to be based on our 24 electrons. So we're going to put our carbon in the middle. That's always where we're going to start. So when you're like, well, how do I start a Lewis structure? You always start with your least electronegative atom, and that goes in the center. So you're going to start with carbon. Then folks kind of vary in their approach here. And so I think this is a great opportunity for you to practice and figure out what's the best fit for you. I have a tendency to use the patterns that we just talked about and start there. So for example, I would start with a single bond to oxygen, a single bond to oxygen, and then, right, maybe you put a single bond to oxygen here, but you're going to start counting electrons and realize, ooh, I actually need 2. So we're going to put 2 bonds here to oxygen. So if I think about it and I count up electrons so far, because each bond is worth 2 electrons, that's 2 electrons between oxygen and carbon. So that's 2, 4, 6, 8. So I've used 8 of my valence electrons so far. Now I need to think about the other 16. So that's where I then distribute my electrons to satisfy the octet rule. So I'm going to put electrons around oxygen until it has 8 electrons. So 1 lone pair, 2 lone pair, 3 lone pairs. So that's a total of 6 electrons plus the 2 electrons from the bond. So now oxygen's octet is satisfied. I'm going to do the same thing for this oxygen. Notice, right, they're identical. So if I've already done this over here, I'm just duplicating that here. But again, if I think about my process, it's 1 lone pair, 2 lone pair, 3 lone pair, plus the 2 electrons that are in the bond. So again, that gives oxygen a total of 8. This oxygen, right, is a little bit different. In this case, it has 2 electrons from this bond, 2 electrons from the other bond in the double bond. So that's 4 electrons total. It's only going to have 2 lone pairs. That totals 4, so 4 plus 4 is 8, and this oxygen has a complete octet. Now, have you ever wondered how they come up with the charge that goes on a polyatomic ion? Well, we're going to calculate that charge right now. So we've satisfied our octets for each of the atoms. Now we're going to use an equation to calculate our formal charge. So in order to know the formal charge, remember, this is always the charge on an individual atom. We're going to look at the number of valence electrons. We're going to subtract, in parentheses, the number of free electrons. So really important here, it's not the number of lone pairs, it's actually the number of free electrons plus the number of bonds. So we're going to go through, and for carbon, right, we're going to figure out, okay, how many valence electrons does it have? Oh, yes, I need to look at my periodic table. I can look at my group number, or I can look at its position in the periodic table. Carbon has 4 valence electrons. Then I'm looking at carbon and I'm saying, hey, are there any free electrons, or are there any lone pairs around carbon? And the answer is no. So if the answer is no, then I just put a 0. Carbon has 0 free electrons or 0 lone pairs. Then I'm counting the number of bonds. So carbon has 1, 2, 3, 4. So that's the number 4 that goes here. So if I then do my calculation, carbon is 4 minus 4, or its charge is 0. Now let's look at another example. Let's look at oxygen. So oxygen has a formal charge calculation that is similar. We're going to use the exact same equation. In this case, oxygen has 6 valence electrons. And if I'm looking at this oxygen, I'm going to choose the one that's on the left. I'm going to count 1, 2, 3, 4, 5, 6 free electrons, because those are the electrons that are in my lone pairs. So that's the reason why I have the number 6 here. And then I have 1 bond between oxygen and carbon. So if I add those up, 6 minus 7 gives me a -1 charge. That's the reason why this oxygen has a -1 charge. The number of valence electrons, right, is exceeded by the number of electrons that are actually available thanks to this bond to carbon. But there are other oxygens, right? So let's look at these two. So if I look at the oxygen that's on the right, it's identical to the one we just calculated. And you can prove that to yourself by going through the calculation again. Oxygen has 6 valence electrons. It has 6 free electrons. And it has 1 bond. So if I, again, do that calculation, 6 minus 7, that gives me a -1 charge. So now there's a negative charge on this oxygen, and there's a negative charge on this oxygen because they have the identical structure. They have a single bond and then 3 lone pairs or 6 free electrons. But let's look at this oxygen. Its structure is slightly different. In this case, it still has 6 valence electrons, but now it has 2 bonds and 2 lone pairs. So if I think about how I fill out this part of my formal charge calculation, it has 4 free electrons. I get that from looking up here. These are my 4 free electrons. And then I have the 2 bonds that are here. So 4 plus 2 is 6. So that means that this oxygen has an overall charge of 0. Now, here's what's really cool. If we're thinking about our atoms and the molecules that they form, it makes sense that if we know the individual charges of each atom, if we add those up together, that's going to give us the overall charge of our molecule. So in this case, I use the brackets to represent the fact that this is the complete molecular structure. What's outside the brackets is telling me, hey, this whole molecule has a net or an overall charge of 2 minus. And I get that because this oxygen is 0, this carbon is 0, but each of these oxygens has a negative charge of 1. So if I add those together, that gives me an overall charge of -2. So before we go further, I want you to think about the steps that we just went through to draw the carbonate ion. Think about what order of steps would make sense for you, right? Sometimes it's easy to do that in shorthand, right? So coming up with the structural formula and then your tally in terms of your valence electrons, and then your least electronegative atom that goes in the center, and then you satisfy your octets, and then you calculate your formal charge. But in your notes, come up with the process that you want to use to do this calculation. take a moment, think about the process that you want to use in your notes to do this calculation. Okay, if you feel like you have a comfortable process identified in terms of the order of steps that you're going to take, then I'd like for you to go ahead and try this one. So you're going to draw the sulfate ion. You're going to determine its formula. You're going to add up the valence electrons. Then you're going to think about the skeleton structure or how you start drawing your Lewis structure. And then you're going to think about octets and formal charge. So take your process and let's apply it to another example. Okay, let's talk through this one and see if we can make sense of drawing the sulfate ion together. So you're probably thinking, what's the formula? And this is usually the moment in time where folks are like, oh, I remember that, right? Or it's the, I don't know that I ever studied that. Or it's the, I think I knew that, but it was a long time ago and I've forgotten. That's okay. Wherever you're at in that spectrum is okay. At this point, our goal is to practice enough so that it comes to mind easily. So if you want to think about this as something that you can set as a goal for this class, there are several polyatomic ions that we want to be able to call to mind because they're going to show up again. For example, carbonate is part of the blood buffering system. So for example, if you were to take the biochemistry class, then you would see carbonate showing up when you're calculating the buffer for blood. Carbonate is going to show up again, say for example, in your upper division courses when, say for example, you're studying ocean acidification and the physiological responses of rockfish to ocean acidification. The sulfate anion is going to be something that's going to show up, say for example, in Chem 111 next semester. So you're going to be calculating the half reactions for sulfate with a number of metals. So we're going to practice until you get to the point where you're really comfortable with the polyatomic ions. So if you're already there, great, kudos to you, that's awesome. If you're like, I am a work in progress, I'm not there yet, but I will be, that's awesome too. So the sulfate ion has a formula of SO4 minus 2. So we're going to add up our valence electrons. Let's think about the process that we use to do that. So we have to go to our periodic table and we have to find sulfur. If you're like, ooh, I don't know where to find sulfur in the periodic table. My best bet is I always look for oxygen and then I go down. That's actually the way that I find sulfur in the periodic table. Is I go across to find oxygen and then I go down. That's great because if I know the number of valence electrons for oxygen is 6, then sulfur has the same number of valence electrons. So sulfur has 6 valence electrons. Then, right, because it's SO4, right, I also have the 4 oxygens. So those have 6 valence electrons too. And I also have the 2 valence electrons from the charge. Now I will tell you, I remember first learning how to do this and I would always forget to include the electrons from the charge. So much so that I finally had to like write a permanent post-it note. You ever do that? Where you're like, don't forget, Corin. Don't forget about the electrons in the charge. So maybe you already know how to do that. If so, and you already include the electrons from the charge, great. But if you're like, ooh, I tend to forget that too, then just make a mental note. Make sure you check, did I include the electrons from the charge? So we're going to add up our valence electrons. And then we're going to think about our skeletal structure. So here are the 6 electrons from sulfur. Here are the 6 electrons from oxygen, but remember we have 4 of those, so we have to multiply these together. And we have the 2 electrons from our charge. When we add that up, that's going to give us 32 electrons. So now we're going to have to satisfy our octet rule using these 32 electrons and figure out how to distribute those electrons to sulfur. So how do we start? Well, we're going to start with our least electronegative atom. Remember, our trend for electronegativity is that it increases going from left to right. So fluorine is the most electronegative. So as I move across my periodic table to the right, my electronegativity increases. It's also true that my electronegativity increases as I move up the periodic table. So anything that is in the same group but below an atom, so for example, sulfur is below oxygen, it's going to have less electronegativity than oxygen. That's the periodic trend for electronegativity. So that means that sulfur should be my central atom because it's my least electronegative atom. So that's what's going to go in the center. Now I've got 4 oxygens that I have to distribute. This is really interesting. I don't know that we're going to talk about this until next week, but when you're drawing your Lewis structures, you really want to pay attention to the geometry or the position of the atoms with respect to each other. This is the way I think about it. I really dislike being crowded. It's probably one of my least favorite things to experience. So I appreciate a little bit of elbow room. Atoms do too. So atoms are going to spread out or distribute themselves so that they have the optimum spacing between them. So if they can spread apart, they will absolutely do so. And that's true in terms of 3-dimensional space. So right now we're thinking about molecules and they look pretty flat, but shortly, in fact, next week, we're going to start talking about how those molecules have very specific defined 3-dimensional shapes. And if you're like, well, why do they have those shapes? Right? What is the reason why they distribute themselves? It all comes down to energy and stability. Virtually everything we know about structure is that it's determined by energy and stability. Either you have to put energy in to change that structure, or it's going to adopt its most stable configuration. And that usually means everything's spread apart as far as possible. Okay, so let's think about then how we would draw our Lewis structure. So we put our sulfur in the middle, and usually we're going to start by drawing a single bond to each of the oxygens. But you can tell already that's only 8 electrons and I have to distribute 32. So at this point, I'm going to add at least 2 more. That's why I have the double bond from sulfur to oxygen, because now I've got 2, 4, 6, 8, 10, 12 electrons that I've accounted for. Now remember, you may have this moment you're like, wait a minute, Corin, I don't know that sulfur, that's more than an octet. That's okay. Sulfur is one of the atoms that can have an expanded octet. So it's okay for sulfur to have 12 possible electrons at a given point in time because it can accommodate an expanded octet. But we've only used 12 of our 32. We still have to distribute 20 additional electrons. So let's think about this. We're going to go ahead and for anything that is a single bond to oxygen, we know that it has to have 3 lone pairs or 6 additional electrons. So we're going to add in our lone pairs for oxygen if it has a single bond. So 3 lone pairs, 1 bond is the pattern. If oxygen has 2 bonds or a double bond, then it's going to have 2 lone pairs, in which case, right, we're able to draw our right? 2 bonds here and then 2 lone pairs on either side of the oxygen. And again, we spread them out so that they're farther apart. In reality, our electrons exist in population densities. It's not like that single dot exists in space and that's where it lives. Our electrons have the freedom to move. So this is just a representation. It's a good example of a model that has benefits, i.e. drawing the electrons means we can see them, but it also has limitations. The limitation of this model is that the electrons aren't always there. Sometimes they move. Okay, the last step is going to be to calculate our formal charge. So if you think about it, we're going to do our sulfur formal charge in the middle to start with. So in this case, right, sulfur has 6 valence electrons, which means that if I'm thinking about, right, the first thing that goes here, remember it's number of valence electrons for the atom. So I'm going to start with 6. Then I'm going to subtract. What goes in my parentheses is the number of free electrons. So in this case, sulfur has no free electrons, so it's going to be 0. Then I'm going to add the number of bonds. Well, in this case, sulfur has 6 bonds. So 6 minus 6 gives me an overall charge of 0. What about oxygen? Well, here's where it's important that I notice how many different types of oxygens I have. I have 2 different types of oxygens. I need to do a calculation to represent each type. So in this case, I'm going to look at the oxygen that has a single bond and 3 lone pairs. So in this case, I'm going to start with my 6 valence electrons for oxygen. I'm going to subtract the single bond to sulfur. Oh, sorry, I think I flip-flopped those. These should be the other way around. Put a 6 here, put a 1 here. Right, so there's 6 free electrons and 1 bond. I'll correct that in the slides with a different color. Again, because these are in parentheses, remember you have to do this operation first. So it doesn't really matter whether you have the number of bonds listed first or the number of free electrons. But for following a pattern, it probably makes sense. So 6 electrons that are free, 1, 2, 3, 4, 5, 6, and then 1 single bond. I'm going to add those together. Right? That's 7. So 6 minus 7 gives me a total of -1. Last but not least, right, I have this double bond to oxygen. So in this case, I've got my 4 free electrons. Remember, you're always counting not lone pairs, but the number of free electrons, and then 2 bonds. So I'm going to add those 2 together, and that gives me an overall charge of 0. Okay. If I'm thinking about my net polyatomic ion, then I want to think about my overall charge. Well, in this case, this sulfur and the 2 double bonded oxygens all have a formal charge of 0. But I have 2 oxygens that have negative charges. I'm going to add those together, and that's my negative charge that goes on the outside of my bracket. Okay, so I want you to take a moment and think about what you know. So at this point, you know, right, how to determine the number of valence electrons. You know how to determine the number of free electrons. So you're just counting up the free electrons. You know how to use patterns to assign your valence electrons to an atom. And your big idea is that you are trying to get to the octet rule. So with the exception of hydrogen and helium, lithium, beryllium, and boron, who all have less than an octet, everything else, you're trying to get to an octet. So if you're thinking about this pattern, right, the pattern is we think about our chemical formula. That's our first step. So figuring out our chemical formula. Then we add up our valence electrons. We do that. You're going to have to use a periodic table, right, and the group numbers to be able to make sense of that, or the position of the atoms in the periodic table. Then we have to figure out our least electronegative atom. If you're like, ooh, I don't know that I remember the periodic trends, this is a great opportunity to think about how you're going to remember that. So your electronegativity always increases going from left to right across the periodic table. Your electronegativity also increases going up the periodic table. So from bottom to top, as you go up the periodic table, fluorine is most electronegative. So all arrows point towards fluorine. So that's the way that I remember that. So I go from left to right, most electronegative. I go from bottom to top to get to most electronegative. And then the last piece that you're going to want to pay attention to is how you calculate formal charge. So again, what's in the parentheses, the order doesn't matter. Number of bonds, number of free electrons, you're going to add those two together. So the number of free electrons is just counting electrons. So 1, 2, 3, 4 electrons, for example, are the number of free electrons around this oxygen. The number of bonds would be 2. So you have to know how to calculate your number of valence electrons, know how to determine your number of free electrons and number of bonds. So delightful news for you. If you can calculate formal charge and you can determine valence electrons, you can figure out just about any kind of chemistry. That's the foundation that will give you, right, a place to start, no matter what molecule or reaction you're given, which is really cool. I feel like it's kind of like cracking the code. So I want you to be really confident doing this process because you're going to do it over and over and over again. In fact, I know that the very first lab that you do for organic chemistry, for example, is writing out Lewis structures, which is this process. So if you can do this now, it means you're going to nail the first exam and the first lab for organic chemistry, and it'll be super helpful for you going into the second semester of general chemistry. So going into Chem 111, if you can draw Lewis structures, you're in a really good spot. So we're going to practice doing one more of these, and this one you're going to do on your own. So I'll give some extra time for you to think through your process for how you determine the Lewis structure and the formal charge for phosphate. And if you've got questions, please don't hesitate to put them in the chat. Michaela asked a really great question about what the B represents. Again, that's the number of bonds, the number of free electrons. If it's better for you, you're welcome to write out that equation with the full words rather than the abbreviation. So whatever works best for you, just let us know. Or put it in your notes, whatever your preference. So if you're watching this as a video, this is a great opportunity to just pause me speaking or fast forward if you feel uncomfortable with the silence because you want to know the answer. You'll have to forgive me. I've got a bit of a stuffy nose today, so I'm constantly sniveling or snuffing. I have a box of tissues here. Don't worry, I don't think it's COVID-19. I think it's literally just my allergies going haywire. So Mackenzie just asked a really brilliant question. She said, how do you know when the center atom needs to have more than the octet? For example, like sulfur in the last example that we did. So this is a really great question because the answer is if it's anything after neon or after atomic number 10, it can have an expanded octet. But for your purposes, the two that you're most likely to see when you're drawing would be phosphorus and sulfur, or anything that are in those groups. So for example, if you're thinking about your periodic table, it would be phosphorus and anything that's below it in the periodic table in that group, or sulfur and anything that's below it in the periodic table in that group. It's a really astute question. So I think it's easier, you're gonna laugh at this, but it's easier for me to remember the things that don't form expanded octets. So I just remember neon and everything less than atomic number 10 cannot have expanded octets. Those are the only ones that satisfy the octet rule. And then everything else, it's possible for it to have an expanded octet. And if you're like, well, how do I know when? I usually start by trying to complete an octet. And then if I have more valence electrons that I need to satisfy, then I expand the octet. Okay, so let's take a look at an example. So for our phosphate ion, it's important that we remember that it has the formula PO4, right? And then it has a charge of 3 minus. Right? So in this way, it's a different polyatomic ion than the other two examples that we've looked at where they had charges of 2 minus. This one has a charge of 3 minus. So phosphorus has 5 valence electrons. There are 4 oxygens, and each of them have 6 valence electrons, so 4 times 6. And then I have my charge of plus 3. So 5 plus 3 is 8. 8 and 24 gives me 32 electrons. So if I think about then my skeletal structure, my least electronegative atom has to go in the center. Well, in this case, I can tell just by looking at my calculation, right? 5 is less than 6. So that means that my phosphorus has to go in the middle. Folks sometimes try and skip step 2, right, in terms of calculating the total number of valence electrons, but it's actually, I think, critical to the process. You don't want to skip this step because that's how you make sense of how many valence electrons you have to start with. Okay, so let's take a look then at how we distribute those electrons. Because sometimes folks are like, well, that's great, Corin. How did you know how to draw this? So I put my phosphorus in the middle and I do a single bond out to each of my 4 electrons, or sorry, to each of my 4 oxygens. So that's a total of 2, 4, 6, 8 electrons. But I know that I have 32 electrons that I have to satisfy. So I'm going to do at least 1 bond. Now you're like, well, how come you don't do 2 bonds? Because 32 is a lot of electrons. Well, in this case, because I have an odd number of negative charge, it's a great predictor that I'm only going to want an odd number of double bonds. So that's why I only do one double bond to phosphorus. So right now I've got 10, which is great. Now I have to account for 22. So I'm going to distribute the 3 electrons to my oxygen. So 1, 2, 3, 1, 2, 3, 1, 2, 3. So if I think about that, that's 2, 4, 6, 8, 10, 12, 14, 16, 18 electrons so far, but I need 22. So I'm going to put the other 2 lone pairs on my oxygen. Now at this point, if you were drawing this Lewis structure, right, all you would know is the overall net charge is negative. But you can look at this, and I think based on the patterns, you could predict where your negative charges would go, right? You know that your negative charges are going to go on each of these 3 oxygens because they look just like the oxygens in the previous example. So if I go back to SO4, right, a single bond, right, with 6 electrons or 3 lone pairs looks just like the one that I'm looking at for phosphate. So each of these would then have a negative charge that's associated with it. But if you're like, well, how do I know that it's a negative charge? That's where calculating your formal charge comes in. So take a look, right? I've got my formal charge. Remember, this is of a single atom. I have the number of valence electrons minus the number of free electrons plus the number of bonds. And remember, if it's in a parentheses, we do that first when we're doing our calculation. So let's take a look at the formal charge on phosphate. It has 5 valence electrons. It has no free electrons, and it has 5 bonds. 1, 2, 3, 4, 5. So 5 minus 5, that gives me an overall charge of 0. Let's take a look at oxygen. Its formal charge. I'm going to look at this oxygen. You could have chosen this one or this one. It wouldn't matter because they're all identical in terms of structure. I start with 6 valence electrons. I subtract the number of free electrons, right? 6. And I know it's 6 because I have 1, 2, 3, 4, 5, 6. And the bond. So I have 1 single bond. So 6 minus 7 is equal to a negative 1. So that's why each of these oxygens will have a negative 1 charge. When I ask you to show a formal charge calculation, if you have a type of bonding structure that's repeated, so for example, a single bond between phosphorus and oxygen, and then 3 lone pairs, and you have 3 of those, you only have to show that calculation once. All right, let's look at our oxygen that has the double bond. So our oxygen formal charge is 6. I have 4 free electrons, and I have 2 bonds. So that has a net charge of 0. If I think about then, right, my overall net charge for the whole molecule, right, that's going to be an overall net charge of 3 minus. Why? Because my oxygen here is 0, my phosphorus is 0, and then each of these oxygens has a negative 1 charge. Okay. So in the email that I sent for class today, I included a worksheet, and I want you to do that practice before you come to discussion tomorrow, because that practice will really set you up for success and help you with asking questions to make sense of how to draw Lewis structures. Before we leave today, I've got 2 pieces of information that are really critical that I want to share with you. Next week, we're going to be looking at drawing different types of Lewis structures. You're like, what do you mean different types? Well, there are certain molecules that could have more than one form of a Lewis structure. So for example, there's more than one right way to draw a Lewis structure, but that distribution of electrons, again, is subject to stability. So it's not always the same. So you can draw different Lewis structures, but there might be ones that are more preferred than others because of their stability or because of their energy. And so we're going to look at that and start to talk about why you would prefer drawing one versus another Lewis structure for the same molecular formula. We're going to look at resonance, and we're going to make sense of reactivity. But all of that is contingent upon your ability to draw Lewis structures. So that's where we're going to focus our practice for discussion tomorrow. This idea of analyzing and interpreting data, what you're doing right now in terms of drawing Lewis structures is modeling. You're modeling the information from the periodic table for an atom. Right now we're doing that and it's flat, right? It's something that doesn't have shape. Next week, we're going to start thinking about the three-dimensional shape of molecules, which is another reason why it's really important that you're super comfortable drawing Lewis structures. Okay, last but not least, so we talked a little bit about what we're going to be doing in discussion. I should say, I know that life is so much in flux right now. So if you're originally assigned discussion time of, say, for example, 8 o'clock in the morning does not work for your schedule, that's okay. You're welcome to come to the 3 o'clock or the 4 o'clock session. If your 4 o'clock session, say, for example, conflicts with work for you, then come to the 8 o'clock session. You have the flexibility. I will assign the points as long as you come to at least one, right? And the way that I do that is both by looking at your participation during the discussion section and your completion of the exit ticket. Okay, last couple of minutes of class. I really want you to start thinking about some of these goals. So if you haven't had a chance to go back and check out your learning chemistry workbook, you're definitely going to want to go there because that is worth an exam score. And we are in week 12 and it is due in week 16. So essentially a month from now, that workbook is due. And so when you think about your goals or how you think about your thinking or reflecting on your learning, that workbook is really the space where you most often do that. I had someone ask me the other day, they're like, why is that slide still in all of the lectures that we do? And it's actually because I think it's the most important component of the work that you're doing in order to make sense of learning chemistry. So there's a ton of evidence out there that says that unless you set aside time to reflect on your learning, to go back and say, okay, did that make sense? Yes or no? Am I still confused? Do I need clarification? Without that process, you don't transfer that knowledge. So for example, when it is 6 months from now and you are taking Chem 111, you're gonna be like, wait, what's the formula for sulfate? Whereas if you incorporate time to reflect and think about your thinking, you're more likely to transfer that knowledge to new contexts and new situations. So, exam 2, we're going to continue with chapter 7 next week. And then if you haven't yet taken exam 2, don't worry, you'll get an email from me during your time block. In fact, I've got a whole bunch of emails to send out for the folks who are taking it at noon. And then if you have already taken it and you haven't gotten a score yet, thank you for being patient. I will get your exam score to you literally as soon as I possibly can. So with that, I'll hang on here for a couple of minutes in case there are questions. Please don't hesitate to ask. Otherwise, you are free to go, and I will see you for discussion tomorrow.